We talked about translational motion. We went from first defining what is position, displacement, velocity, and acceleration. And then we went to the special case of constant translational acceleration. We're going to do the same thing with angular acceleration. And what's so nice about this is essentially the transformation from translational motion to rotational motion is really, really easy. We're just going to swap out our variables. We're going to change x, which is our linear motion or translational motion variable for position in one dimension, to just theta. We're going to trade out displacement delta x with delta theta. V0 just becomes omega 0 for initial velocity, and our final velocity just goes from v to omega. And again, our problem with acceleration, a looks very much like alpha, but we are going from essentially letters to Greek alphabet letters. And again, the units, with position, we go from meters, which has the dimension of length, to dimensionless units, radians. And then initial velocity goes from meters per second to radians per second as its final. And then finally, we're going to replace our acceleration meters per second squared to radians per second squared. Okay, so here's what's really nice, because we've learned this already. We've learned these kinematic equations earlier on in the semester, earlier on in course. So our equations, we're just swapping out these variables. V final equals V initial plus AT, again for constant acceleration, just becomes omega equals omega naught plus alpha t. Okay, nothing hard really there. You just have to get used to that, the fact that V's become omega and A's become alpha. And we can do the same thing for our average velocity, initial and final, to get our angular displacement. This equation we use quite a bit for one-dimensional motion. Our displacement is equal to V initial times time plus 1/2 AT squared. Now that just becomes theta is equal to omega naught t plus 1/2 alpha t squared. And then when we don't have time, V squared is equal to V naught squared plus 2ax. And now omega squared, our final angular velocity squared equals our initial angular velocity squared plus twice the angular acceleration times the angular displacement. You don't need me to read all these out. But again, we are going to do problems just like we did before with kinematics. We're going to identify what we know. We're going to identify what we're looking for, and then try to find an equation that has both our knowns and the quantities we seek. So for instance, let's say we have a wheel that rotates with a constant acceleration, 3.5 radians per second squared. Just think about this the same way you did with the other kinematic equations. You'd be given an acceleration, maybe 3.5 meters per second squared. Okay, so we know it has an acceleration. We're given that. The angular speed of the wheel is going at 2.0 radians per second initially. What is the angular speed after 2 seconds? So we know our initial angular velocity, we know our angular acceleration, we know our time, okay? This is the only equation out of all of those that works for this. This doesn't work because angle is unknown and time is unknown. This doesn't work because omega is not known and angle is not known, okay? So this one works. And in fact, all we need to do is plug in our values. Initially, 2 radians per second. Our acceleration, 3.5 radians per second squared. Time, 2 seconds. Okay? 3.5 times 2 is 7. 7 plus 2 is 9. Very easy to do. Okay, that wasn't hard. The equation didn't even have to be manipulated. Through what angle does it rotate? Again, we're just plugging in values here. Now we want to find the angular displacement. We know the initial velocity, we know the time, we know the angular acceleration. We're just plugging in values for these. Okay? 2 times 2 is 4. 1/2 3.5 is 1.75 times 4. 7. So 7 plus 4 is going to give me 11 radians for rotation. Okay? And always check back to make sure that this makes sense. One complete rotation is 2 pi. That's roughly 6. So this makes almost 2 complete rotations. Yeah, that seems reasonable. If we're going 2 radians per second and we rotate for 2 seconds, if it hadn't accelerated, that would represent about 4. But with the acceleration, we get an extra 7 here. Finally, the wheel is initially rotating at 9 radians per second. Now we're going to slow it down. A braking force produces an angular acceleration of -20 radians per second squared. Here, we have to manipulate the equation. We're given the final speed. It's going to be 0. We're given the initial. We're given the acceleration. We need to find out how much it rotates before it stops. So we solve here for, given that omega squared is going to be 0, we solve here for theta in terms of omega naught squared and the acceleration, and we get 2 radians of rotation for this case. Okay? So again, not much review has to be done for this. Just get comfortable with swapping out the variables. Same exact approach. What are our givens? What are we looking for? Which kinematic equation works? But we have to understand for this case, it's a special case where only for constant angular acceleration will this happen. Now, later on, we're going to talk about force and torque. We could use the kinematic equations for translational motion when this acceleration was constant. And that normally was constant when our forces, our net force was constant. And that's why, we could use that for so many situations. We are going to look at the rotational analogy. Our rotational force, we will find, is something called torque. Torque is usually represented by this Greek letter tau. Okay? I replaces m. M was our mass. Mass is a measure of inertia. We will have something called rotational inertia, or more commonly known as moment of inertia. So force is replaced with torque. Mass is replaced with moment of inertia. That's related to how the mass is distributed with respect to the radius from the axis of rotation. And angular acceleration replaces acceleration here. As long as the net torque on a system is constant, and you've got to be careful here because we can change the moment of inertia pretty easily by redistributing the mass from the axis. As long as these two are constant, obviously the angular acceleration is going to be constant, and we can use those kinematic equations. Okay, so again, this is going to be another version of Newton's second law, but for a rotating body, and that's when the kinematic equations can be used. So again, kinematic equations are useful when we have something constant, such as the acceleration. We're just making the angular acceleration constant here.